session. First up, by Jack, who will tell us about Rado numbers.
Thank you very much to the organizers for the invitation to speak. This talk will have 3 parts. The first, I will give some mathematical background and some history and motivation behind some of the objects we study. Then I will discuss 2 projects. The first is more of a practical SAT application to the Rado numbers. And then the second deals with Nullstellensatz certification for Ramsey type numbers. And I'll try to describe some connection between the 2. Okay. So as many of you know, of course, Ramsey theory can be described as, study of patterns that appear when you have a sufficiently large mathematical object, or patterns that are preserved when we partition or color that object. And the most famous result in this area is, of course, Ramsey's theorem, which says that if you red-blue color the edges of a large enough complete graph, then you will necessarily find either a red KR or blue KS. What is not as well known is that there are sort of Ramsey theorems that actually predate Ramsey himself. And these are not, these did not start with sort of logic, but they actually had their origins in algebra and number theory. What might be argued to be the first Ramsey type theorem is called Hilbert's cube lemma, which I've written in this form. It says that for every number of colors k in dimension d, there's an n where if you k color a large enough interval 1 through n, you will find a monochromatic solution to this system of equations. And the system sort of describes an affine cube of integers. And Hilbert proved this while he was studying irreducibility of rational functions, so more of an algebraic motivation. And the joke here is that it's a shame that Hilbert didn't really study these coloring principles further, otherwise he could have been famous. Moving on, the next main result in this area is Schur's theorem, which says that, again, if you k color a large enough interval 1 through n, then there must be this monochromatic triple or monochromatic solution to this equation x plus y equals z. And Schur proved this while he was trying to attack Fermat's last theorem, and he used this to prove things about solutions to this Fermat equation mod p. And often in Ramsey theory, we're interested in the smallest such n that works. And in this case, we call this smallest n the Schur number Sk. Okay, so just as a few very simple examples of this, S of 2 happens to be 5. It's not hard to convince yourself that if you color 1 through 4 in this way, then you avoid monochromatic solutions to x plus y equals z. But it turns out no matter what you do for 1 through 5, you will get stuck. And you can keep going. S of 3 is a little harder, but still doable, by hand. You can 3-color 1 through 13 while avoiding solutions, but no matter what you do for 1 through 14, you get stuck. And I will say a bit more about the other known Schur numbers in a little bit, but I want to sort of finish this historical story. The next big theorem was van der Waerden's theorem. It says, again, if we k color 1 through n, then you will necessarily find a monochromatic length L arithmetic progression as long as n is large enough. But rephrased in this way, you can also view this as you must find a monochromatic solution to this system of equations that describe an arithmetic progression. And again, there's a number theory motivation. This was conjectured by Schur while studying quadratic residues. And like the Schur number, we can define a van der Waerden number to be the smallest n where this works. And again, as a small example, W23 is 9. These are essentially the only 3 colorings that you have, but you get stuck at 9 in each case. And you can keep going with this as well. Their best known general bounds for these numbers, the best Generally, the best accepted lower bound is this finite field construction, and the best known upper bound is this funny looking power tower due to Gowers, which actually uses some very deep and difficult results. In terms of exact values, we also don't know very much. We only know these 7 as far as I'm aware. So this is hard both from an asymptotic standpoint and a computational standpoint. Okay. So I've sort of phrased these 3 theorems suggestively. I phrase them all in terms of equations. And so a natural question is, okay, what about other systems of equations? And is there a way to sort of put these 3 theorems under one umbrella? And the answer is yes. And this was largely answered by Rado in his first PhD thesis, which was with Schur. Okay. So again, we will define what's called the Rado number for an equation. And this is going to be the smallest n for which we necessarily find a monochromatic solution to the equation with k colors. And in this language, the Schur number is just the Rado number for x plus y equals z. But Rado numbers behave slightly differently in general. It turns out they don't really always exist. So for this equation, 2x plus 2y equals z, the 2-color Rado number happens to be 34. But for 3 colors, you can actually 3-color all of the positive integers while avoiding these solutions. And in this case, we say that the number is in infinity. And I need one more definition. We say that an equation is regular if the k-color Rado number exists for all k. So Schur's theorem just says that the equation x plus y equals z is regular. And Rado's single equation theorem is sort of a direct generalization of Schur's theorem. So it's that if I write my equation in this form, then this is regular if and only if there's a non-empty subset of the coefficients that sums to 0. So something like this is regular. So 4 plus 3 minus 7 is 0, but something like this is not. Okay. And I'm sort of going to stop here, though I should mention that the full version of Rado's theorem does indeed capture systems of equations. And from Rado's full theorem, you can deduce van der Waerden's theorem and the Hilbert cube lemma, among many other things. Which one?
How was the Hilbert one? Oh, no, it was one variable plus sum, or what was it?
This one. It should be homogeneous.
X0? X empty set. What is it?
Yeah, x0 is just sort of this affine shift. So yeah. Okay. Any other questions? Okay. So what does this have to do with SAT? Well, there's been most of the best bounds for these numbers, or exact values for these numbers, are due to SAT solving. This is going to be just a non-exhaustive but decent list of some of the successes SAT has had in computing these numbers. So some of the first were was this van der Waerden number, W26. And from there, there's a lot of study of other various generalizations of van der Waerden numbers. Green tau numbers has to do with arithmetic regressions over the primes. And then there's another exact value for this van der Waerden number, and many other various generalizations of this. And Myers, in his thesis, did a very systematic study of Rado numbers and used a lot of computational techniques that included. And there's also, I did not define this, but this 3-color Ramsey number also used a bit of SAT in it. And then the last 3 are sort of most relevant for our results. The Pythagorean triples problem, that was the Rado number for x squared plus y squared equals z squared, the two-color case. And Schur number 5 was done in a few years ago by one of our audience members. And then there's also this result on what are called generalized three-color Schur numbers, which are a type of Rado number done in 2019. So based on all of this nice work, we decided to use that to study the Rado numbers. So I want to go back to Schur numbers first. So this is a table of all the known Schur numbers, and we're stuck at 5. And Schur number 5 proof, particularly the upper bound, was the massive stats computation using cube and conquer, and produced arguably the largest proof ever created. And this was our main motivation for doing this. But okay, so there are sort of many ways you can go with Rado numbers. It's not so obvious what should be studied. But we settled on this case, this 3-variable case. 2 variables is not so interesting. It's totally known. But 3 variables still has a lot of unanswered questions. So this equation, ax plus by equals cz, the Rado numbers. So this equation will give you upper bounds for any other homogeneous equation with more variables. And the 2-color numbers are the most popular. These have been studied by far the most often, but we still don't have a general formula for ax plus by equals cz. However, if we set some of a, b, and c equal to each other, then we do have exact formulas for these 2 cases, although they're still a bit complicated. This ax plus ay equation still has sort of 14 different cases. But relatively little was done with 3 or more colors, so we thought that this was a good place to start. So this was sort of our initial computation. Excuse me. We did lots of computations. For 2 colors, we went for the most general case and got a couple thousand of them. And we sort of lose an order of magnitude with each color added. We got a few hundred 3 colors and like 10 or so 4 colors. So this was the beginning. And looking at one of these tables, this is what we found. So this is for a times x minus y equals bz. And we got this table. And I've highlighted 3 patterns. So this first pattern is this blue upper triangle here. And it's not hard to see that all of these values are equal to a cubed, unless a and b are not relatively prime. And this green diagonal also has a nice easy formula. It's a cubed plus a minus 1 squared. And this first column, this red column, also has a nice polynomial description, though perhaps not as obvious. So natural question here obviously is, okay, do these patterns continue? And the answer is yes. Yeah, we just sort of looked at it and guessed, yes. Or I think the first column we just threw into the yes. And so the question is, does this continue? And the answer is yes. All 3 of these patterns do indeed go on. Okay. And I should mention that this last result was conjectured by Myers in his thesis, and it implies this other conjecture on these generalized Schur numbers. The generalized Schur numbers are just it's the Rado number for an equation that looks like the Schur equation, but with more variables. And this was proven in 2019, although our result is slightly stronger. Okay, so how do we do all of this? So for our previous table of this, we just did a natural stat encoding, but I also want to explain how we do this as well using stat. So just the basic setup is, of course, given an equation E, we construct a formula where it's satisfiable if and only if the Rado number is at least n. And I won't spend too much time on this encoding, but we have variables for each integer color pair, where this variable is set true if and only if we color I with color C. And borrowing the language of the Schur number 5 paper, we use 3 types of clauses, which we call positive, negative, optional. And positive clauses just say that each integer gets some color I. Negative clauses sort of forbid monochromatic solutions. So we have a clause of this form for each solution in each color C. And optional clauses just say each integer gets exactly one color. Here's just a simple example using the Schur equation, 3 colors and 4 variables. So for all these numbers, we just produced a satisfiable formula at n-1 and an unsatisfiable formula at n, and this is enough to show the Rado number is equal to n. And what we did was just, for each of these, we essentially just guess and then binary search our way to n. And solving actually turned out to be very, very fast. We just used out-of-the-box solvers, mostly canonical towards the end. And for 2 or 3 colors, these essentially everything can be done in under a minute. But for 4 colors, we do some basic symmetry breaking, and it requires a bit more time. But sort of our main result is modifying this to compute infinitely many values using a single formula. So it all sort of hinges on this observation, which I will use this as a toy example, is that we don't need all of the integers in our proof. Not only do we not need like all the clauses in the formula, but we don't need all the integers. So here's how you could prove that the upper bound here is 9. So about loss of generality, we can say 4 is red. Then we have this solution 646, says 6 must be blue. And then if you keep going, okay, we have 969 and 334, which force 93 to be red and blue. But then you're stuck, of course, at 7. But we did not need to use all the numbers 1 through 9. We could throw out 1, 2, 5, and 8, and the proof works just as well. But what we want to do is to describe a set like this S that works for this entire family, right? So just to do another quick example, this 2-color number for this family is known to be a squared minus a minus 1. And we can use this set S to prove it for each a. So again, you can go through this proof. If 1 is red, this forces a minus 1 to be blue. And then this forces a minus 1 squared to be red. Then we will get a contradiction fairly quickly. And this actually sort of looks like the proof for S of 2 less than or equal to 5, with these polynomials playing the roles of 1, 2, 3, 4, and 5. Okay, so what we can do is prove these upper bounds by generating a formula in the same way using these polynomials. It's generated exactly the same positive and negative, or positive and optional clauses, but now our negative clauses will look something like this. And these sets S will describe an unsatisfiable core, or family of unsatisfiable cores for this family of equations. What we were able to do is we found suitable sets S for our families, and we're able to get these upper bounds in each case, and the solver does it very fast, in less than 10 seconds each time. I should say that you have to be a little bit careful the polynomials need to be bounded in a certain way. They need to be bounded between 1 and the upper bound for every value of a or b that you might plug in. And yeah, the way we generated them was a bit messy, a bit complicated. So I don't want to get into that here, but I can say more if anyone is curious. Okay. So yeah, so that was pretty much it for this first project. But we have much more that we're currently working on. So this is known, or this generalized Schur equation, as I said, this is known for the three color case. 3 colors, this is known to be m cubed minus m squared minus m minus 1. But based on our experiments, it is very likely that this is the analogous thing for 4 colors holds as well. But what we really want to do is, refine these methods to find these sets S, these unsatisfiable cores. I said we don't really like the way we did it. Right now, we want to either find a better computational method, or use some math trickery to really describe these minimal sets. Okay. And there's plenty of other places you can do the exact same thing. There are tons of other families of Rado numbers that have been studied. Non-homogeneous cases have showed up a lot in the literature, and you can do this with nonlinear or equations over other billion groups as well. And using this big database for, I should say database, but data for ax plus by equals cz, seems like we should be able to use this somehow to get some insight on a general formula for the 2-color case. Ahead of time, so I will say a little bit more about the other half of this paper, which is more mathematical. But another sort of interesting facet of this is called this degree of regularity, which is defined to be the largest k for which we get a finite Rado number for a given equation. And this is not so well understood, and we're able to get the degree of regularity for a small number of equations, and prove some other results that determine degree of regularity for families where some of A, B, and C are set equal to each other. But this is generally very poorly understood. Rado was able to characterize 2 regularity of homogeneous linear equations, but absolutely nothing is known for 3 regularity or higher. And this relates to what is called Rado's boundedness conjecture, which says essentially that if you fix the number of variables, then either your equation has to be regular, or there is a bound on the degree of regularity. And this is very difficult as far as anyone knows, and we only know the 3-color case where it is shown that delta equals 24 is good enough. But based on our computations, it seems plausible that you can knock that delta down to 4. We don't know if there is any equation with degree of regularity, or equation of this form with degree of regularity 4 or higher. Moving on to the next project, I want to first go in a totally different direction and talk about Nullstellensatz. So we want to sort of understand Ramsey theory and Ramsey type problems through the lens of polynomials in the Nullstellensatz. And we can encode, for instance, a Rado number using a system of equations as well. This is an encoding over F2, or the algebraic closure, where we sort of have the analog of positive, negative, and optional clauses again. Say this middle set of equations says that each variable 1 through n gets some color, and then this first set of monomials forbids monochromatic solutions. And then if you want, you can include these equations as well that forbid integers from having multiple colors. This has no solution over F2 exactly when the Rado number is at most n. And again, as a simple example, you can do this with the Schur equation, 2 colors and 5 integers. So, and I'm using x and y for clarity instead of 2 subscripts. But this system of equations will have no solution. And of course, I won't spend too much time on this, but Hilbert's Nullstellensatz, of course, says that the system will have no solution exactly when we can find this identity, sum of beta I times fi equal to 1. As a Nullstellensatz certificate. And here we were interested in the degree as our complexity measure, and we define that to be the maximal degree among the beta I. And our goal here was to describe Nullstellensatz certificates for Rado numbers, but also for other Ramsey type problems more generally. Okay, so this is something that looks totally different at first, but this is sort of how we describe these certificates. So sort of these Ramsey type games have been well studied. And this one is called the builder painter game. And I will describe it for Rado numbers. So we have a fixed equation E and positive integers K and N. And how it works is these 2 players take turns. Each turn, builder will select some integer 1 through n, and then painter will color it some color 1 through k. Builder's objective is to create a monochromatic solution to E, and painter is trying to delay this as long as possible. So this number, RK tilde, which we call the online Rado number, is going to be the smallest number of turns where builder is guaranteed to win. And note that builder will necessarily win as long as n is at least the Rado number. So as a simple example here, so remember this equation x plus 3y equals 3z. If I play this on the sort of board 1 through 9, then I claim that this online Rado number is at most 5. Because as I showed, builder can just choose from 3, 4, 6, 7, and 9 and still win. So there's a gap between the Rado number and the online Rado number in this case. And this will hold more generally. This will hold more generally. So the same sort of thing will hold for these families of equations that I mentioned before. Okay, but our main result here is that using this F2 encoding, there is necessarily a Nullstellensatz certificate of degree at most this online Rado number when n is exactly equal to the Rado number. But it turns out there's sort of nothing special. There's nothing special going on about the Rado numbers here. This holds far more generally, and you can do the same construction for any Ramsey problem, really. It'll work for classical multicolor Ramsey numbers. It'll work for these numbers I've been talking about. It'll work for van der Waerden, Hales-Jewett, and so on. So I am little under time, but current work and future work that we want to do is to really study the lower bounds for these Nullstellensatz degrees. We don't have any good result in this area, and it may very well be that these online Rado, online Ramsey numbers are really terrible. We don't know. These inequalities, we have examples where each of these are strict. For example, for the Schur equation for two colors, the Nullstellensatz degree is 2, but the sort of online number and Rado number are 5. So we don't really know anything about sort of how tight these inequalities are. And we suspect that there is a large gap in each case. So what we're doing now is sort of approaching it from one direction and trying to understand this builder-painter game for Rado, but also other numbers such as van der Waerden and Ramsey. There are some results that are already known for Ramsey. You can sort of save n log n edges in the online version, but we don't know if that's the best or sort of how well we can do in general. Okay. Yeah, sorry, I went a little fast, but thank you.
Thanks. So I really like your idea also of this set S to compute this. And I was wondering also for these online numbers, did you try to use proof minimization to get unsatisfiable cores to compute this?
We haven't tried anything like that.
Yeah, because I expect that this can be actually quite helpful for this kind of setting to really see, okay, which are the numbers that were used by the solver, and then to kind of generalize it to compute your set S or to minimize this online number.
Yeah.
Oh, great.
I guess to follow up on that question, is there any theoretical reason why there should be these small subsets S that? Why do you know why there's these small subsets S to give you unsatisfiability?
Right.
Lower bounds?
No, that's what we're trying to understand a bit more. It seems like, yeah, that's what I wanted to mention. We sort of don't know what the sort of hard Rado numbers are, because it seems like for sure, like x plus y equals z, you really do need sort of most or all of the numbers all the time. One sort of simple reason, if I go back, here, yeah. So one sort of obvious reason here, we have x plus 3y equals 3z. Well, this, if you rearrange, you can see that x is always a multiple of 3. So we have a bit more structure there with the modular conditions. But it's not so clear how to sort of make this more general or say anything more.
I was also wondering, have you studied these numbers where, so you have n now, the limit that you have, right?
Yeah.
But going beyond that, right? Because for example, I noticed with the Pythagorean triples that if you have a way higher number, then the numbers that you use can get substantially smaller.
Right.
So is there also what's the smallest notion in case you kind of go almost into infinite?
Right. So I guess we haven't studied this with these equations necessarily, though I will mention, I go back here. So if I So I sort of defined these numbers where you're sort of playing on a fixed board 1 through n, right? But you could also study the same thing where you can allow or arbitrary n or all of the positive integers. And for Ramsey, for the Ramsey, online Ramsey, it is known that if you allow sort of infinitely many vertices, then you can get an exponential improvement there. But then it is not known exactly how quickly that goes back down when you go to the actual Ramsey number. So that's one thing we are working on to study this sort of thing when n is much larger. But we don't have anything concrete to say at the moment.
Yeah, cool. Because at least I saw for the Pythagorean triples, I noticed that you can get way smaller. And the question is, I think I increased n to over 1 million, and then I got, I think, yeah. So the proofs get smaller and smaller. I think the proof got out to 1 terabyte, which is still reasonable. But the question is, I say, if you would go to 1 billion, right, or whether you actually might be able to get a human understandable kind of argument for these kind of more difficult cases.
Yeah, we haven't tried that, but I think we will. Yeah.
Okay, thank you.
Any further questions? Yep. The Rado numbers case, is there an explanation why there should be polynomials in the coefficients?
Yeah, that's a great question. Or I guess you mean polynomial. This
is polynomial in the number of variables,
right?
Which you
right.
could also consider.
Or
But all the other examples you gave were polynomials in A and B.
Right. Yeah, I don't have a good answer to that, but that is not true in general. Like Schur numbers are exponential. But yeah, I should say Schur number and some other equations do grow exponentially. But yeah, we don't know.
Hey, well, thank you. Next speaker will be